Who loves or hates ORMs? Who loves them? Oh, few. Who hates them? Got a few. Most people a little bit in between. Well, it's kind of interesting. So why is this kind of interesting debate come up about ORMs quite often is because most of us program in object-oriented programming languages, and we put stuff in a database. Databases work on set theory, relational theory. So there's an impedance mismatch, and so putting these things in and out of the database becomes a tricky thing to deal with. What if we could get rid of that problem? What if our normal objects in Java, C++, C#, whatever it happens to be, could just exist in that language and we didn't have to worry about putting them in the database? Well, in most financial systems and gaming systems, this is the case. But we've got some issues. What if the machine crashes? How do we turn it on and off again? These sorts of things become an interesting problem. So there's ways around that. And a lot of this stuff has been around now for many decades. Like going back to the 1980s, we talked about replicated state machines. And there's some fundamental theory behind that. And that's a little bit of what I'm going to cover today. So imagine we have got some code. It's state machine effectively. Whether you think you're doing state machines or not, you effectively are. You just may not be doing them particularly well or not. If you've got code, you have effectively got a state machine. It may be more complicated than it needs to be, but if we apply inputs to a state machine, it ends up in a resultant state. And so say that those inputs were a series of messages. So we've got messages arriving 1, 2, 3, 4, 5, 6. If we apply them to some sort of state machine, some code that we have, and we apply that to an in-memory model, we end up with the state of our system. As a relatively simple way of working. This state of the system, if we can replicate it on another machine, we're fine if we have a crash. So if the one machine crashes, another machine can take over. This is pretty much how all of the financial systems around the world that do stock trading or trading on FX instruments or anything works is they don't tend to use databases. They keep these things in memory, they run very fast, but they also have to be very reliable. So what's kind of underneath this and how do we get it working? But it's not the only thing in this space that works this way. Lots of other types of technologies use these ideas, so things like event sourcing, you hear command sourcing, CQRS, write-ahead logs. All of these sort of things are using similar sort of concepts, is where we have a log of inputs. If we apply them to the same code on another machine, we can end up with the same deterministic state if it's single-threaded and the code is deterministic. This doesn't work if stuff is concurrent and we've got many threads and the algorithms we're using are not deterministic. Sometimes non-deterministic algorithms are a bit surprising for some people. Like if you happen to use a hash map, it doesn't always end up deterministically in the same state, even if you do the same numbers of puts and gets, because it can randomize the iteration order. People get surprised by things like this. So you have to work out what is deterministic and what is not. Well, what's behind a lot of this is what's known as consensus algorithms. So going back to a lot of the work of the 1980s, Lamport, Liskov, Ken Berman, various other people did a lot of work on consensus algorithms, and they allow a number of machines to end up in the same state, and based upon being in this state, if we have a failure, another one of the systems can take over. So kind of what is consensus and what's it all about? So I want to kind of cover that to begin with. Now, I'm a person who's dyslexic, so I have trouble with reading. At school, I struggled with a number of things. And one of my coping strategies is every time I hear words that I'm not used to, I go look those words up in the dictionary. And it's been hugely educational for me with our industry, because I think I've realized that most people who work in technology who get to name things don't look stuff up in a dictionary. And that causes a lot of problems. Let's have some simple examples. Sort of random access memory. If you look up what random means, is it's not predictable. When you go to memory, you don't want random access, you want arbitrary access. You want memory at a given location. If someone actually implemented random access memory, it would be pretty useless to us. Why do we do things like this? And don't get me started on software maintenance. We don't oil or grease software. It doesn't wear out. We need to adopt it to an environment. That's a different sort of thing completely. So words program behaviors. Well, what about consensus? Let's look up the meaning of consensus and what it means. Well, in the dictionary, we're looking around things like general agreement, but particularly about being unanimous. That's not typically what consensus is about when we look at algorithms, it's actually the second meaning of consensus is what we take as correct when we're dealing with algorithms. It's about where most of a system agrees on something. So if we've got any dispute over what is a given value, as long as most agree it's something, that is what we'll go ahead with. And that's kind of at the core of most consensus algorithms. So we've got a bunch of servers, and they've got a difference of opinion. They need a vote, and the majority get to win on what they believe the state of the system is. And there's algorithms that underlie this. Now, a lot of people will probably have heard of Paxos. Yes? Hands for Paxos? Keep your hand up if you think that was the very first replication protocol that was available. Got a few people are willing to do that. Do you know that there was one before that, which hasn't had the same credit? Anyone heard of ViewStamp replication? Yeah. Paxos came out in '89. ViewStamp replication came out in '88. Leslie Lamport gets all the credit for starting this work, but the person who actually deserves the credit is Barbara Liskov. She came before that. She did some earlier work. Now, there was a lot of simultaneous discovery around the same time, so it's not really fair to point out one rather than the other. Ken Berman also came up with things around atomic broadcast and other work, virtual synchrony in this area. We had a lot of simultaneous discovery around the same sort of time. Now, what was interesting about all of those implementations at that time is, if you ever try to implement them, they are really difficult to implement. They're difficult to read the papers, they're difficult to implement, and most people make mistakes in how they're put together. I've done this a number of times in the past, and I'm still making mistakes every time I do this. Having some chats earlier with some people, other people talking about how they've tried to implement these things, and they're difficult as well. Now, go forward from the 1980s, until just 5 years ago, there's a paper came out that really changed a lot of how we think about consensus algorithms, and it was this paper. It was talking about a protocol called Raft, and it had a very different goal than the previous algorithms in this space. The goal for Raft was to come up with an algorithm that was understandable, a very different primary design goal. Paxos was not designed to be understandable. In fact, if you look at what is the origin of the name Raft, is it about logs and tying them together? That's what some people say. If you actually read some of Diego's comments on it, he talks about Paxos is named after an island in Greece. The raft is your means of escape from that island to get away from that complexity. So there's some interesting history here. Now, this paper is a kind of interesting paper to read. When I first read it, I was very impressed. It was the first that was genuinely understandable. Since then, I've had a go at implementing it. I've also discovered it's very much incomplete. Like most things in this space, they're not a specification. They're an outline of the problem space and an approach to it. They're not a full specification for how to address it. Like this paper would not make it as an ITF spec. I've talked to Diego, how could this be better? Some of the things I found in trying to implement it being difficult, and he pointed out, yeah, we did consider that, but we didn't put it in the paper. It's in my PhD thesis, so I went and read his PhD thesis, which is 5 times the length of this, that has much more detail, but even it is still not complete. These things are complicated, and there's a lot to be done. So this is about as easy as it gets, and yet it's still pretty complicated. Now, a couple of years after that, this paper was produced by Heidi and co. at Cambridge, where they looked at Raft and they looked at if people tried to implement this, did it actually live up to the claims? And they made a couple of interesting discoveries. One being, it was easier to implement than Paxos, and it was easier to teach to students. The most fascinating thing I found about the discovery in this is, whenever they were teaching people, they tried one group of students that taught them Paxos, then they taught them Raft. A different group that taught them Raft first, and then Paxos later. What they discovered that is if you teach people Raft first, you can then teach them Paxos later. It becomes something you get your head around. It's an easier introduction to it. They also discovered that a huge number of students who learned Paxos first and then tried to learn Raft or other protocols later were not able to learn any other protocols afterwards. Paxos damaged them to the point where they weren't able to learn later. This is not good for the industry. We've got to get a bit better than that. My personal history to some of this is, whenever I read the original work on Raft, I found it incomplete and I found some parts of it vague. There's actually some paragraphs in it. The English if you read it, it's very easy to interpret it as to do absolutely the opposite of what they mean you to do. So there's those vagaries and mistakes in it. I was able to understand which way some of those vagaries would go by having read the ViewStamp replication papers, Lifscott's work as well, which is, I think, much more formally specified and clearer. It's a little bit harder to read, but also the revisiting of that has gotten much better over time as well. So there's a lot has been learned over the histories, and we get kind of better at this. So if you've not looked at Raft, what is it in a nutshell? At a high level, it's a fairly simple protocol, and it kind of covers two parts of the whole problem around consensus and having ordered logs. One is electing a node to become the leader, and the other bit is how do we replicate those logs from the leader to the followers. Now, Raft itself, each node is very simple in that it exists in only one of three roles. It can't have any other roles inside a cluster. So you start off in an initial state and you go into being a follower. All nodes must start being a follower at this stage. We have no elected leader. Timeouts occur, and after the timeouts occur, you end up having one or more of the followers propose themselves to be a candidate to be the leader of the system. We have an election at that stage, so they'll all vote among themselves. So who should be the leader? And part of the voting process is to say, here's what I have in my log. I think I have the most up-to-date view of the world. Will you vote for me based upon this? If you win a majority of votes within the cluster, you are elected and you become the leader. Relatively simple. If the leader for any reason doesn't send any messages or send any heartbeats to the followers, it's believed to be dead or not available. What will happen is the followers time out and they'll have an election to form a new leader of the cluster at that stage. So no central control. It's all based upon some really quite cool ideas. Actually, a lot of the cool ideas of this comes right back to work on reliable multicast and how to broadcast messages in clusters from the 1970s. So a lot of these things, they're all built on fundamental work of the past. And if we don't learn from the things of the past, you don't understand why certain decisions are the way they are. So there's really nice ideas in this. Getting away from central control, relying on timers, relying on voting is a very nice way to get a lot of things done in these sorts of systems. So relatively simple. It also has 2 RPC calls. Not a very complicated system at all. So 3 roles, 2 RPC calls is kind of the backbone of this. The 2 RPC calls are, one covers the election process where you request votes. So you send a request vote to other members of the cluster when you're a candidate asking, can you vote for me? And here's my state of the log. If you win that, you go forward into being a leader, and then the leader replicates messages, and it does it via this other RPC call. So very simple, that we can either just ask for votes or we can say append these messages to your log. And when you append messages to a log, you respond with saying, if you're a follower, what messages do you have in your log committed to disk? So it's not just that you've got them, you've successfully committed them to disk so you could survive a failure and move forward at that stage. Sounds pretty easy, doesn't it? Anybody reckon they could implement this quite quickly? 3 roles, 2 RPC calls, job done. If you try this, you start to realize there is a load of edge cases that are not discussed in the paper. I implemented this, and I've been going through correctness testing. We have been correctness testing for a year to get it right. And we still find interesting edge conditions. We have this live in production at a number of places, working very successfully, and yet we still find odd edge conditions. Paxos and other problems that I've implemented in the past, much more complicated, still finding edge conditions in those as well. Programming's kind of hard, especially distributed systems. We kind of working this out as we go. If we implement this correctly, what's nice is it's a formally proven algorithm and it gives us certain guarantees. These 5 guarantees are formally proven. The first 4 relate to how logs are replicated, and the state machine safety for being correct is also a property of the election itself. So we get to have some nice results from this. But how do you understand the vagaries and everything? One of the things I find that's quite nice on this, and it's not really highlighted clearly enough in some of the papers, is some of this is based upon some fundamental functional theory. particularly monotonic functions, is how we can work out how things should be done at different stages. And I wish this was a little bit more clarified in how it's talked about, because it would really help a lot with understanding. I've got a simple way I teach it to people, is that you version all the things. Everything gets a version, then you can start to reason about it. Say you got a message that came around in an election, so somebody passed a vote. Is that vote for the current election, or is it for a previous election? If each election has a version, it's not a problem. If every message that goes into the log has a version, it all becomes much easier. So this is kind of fundamental when you look at all of these problem spaces, is understand that everything has a version and the versions are all monotonic. Then things get to be a lot easier. It makes it a lot simpler to understand. Now, the reason I got involved in this was I've been working on a messaging system for a number of years now. I call Aeron, and people have asked me, are you going to cluster Aeron at some stage? Because people want to have better guarantees in this. What I kind of like about bringing Raft and Aeron together is they've actually got very similar design goals. Raft was designed with the primary goal of being understandable. Aeron had a primary goal to make it easy to understand something and monitor and debug it at runtime. Many people think we built this to become the fastest messaging system out there. That wasn't our goal. Our goal was to produce a system that is as fast as the best commercial products out there. But the primary goal was it had to be understandable and monitorable at runtime, because most of the commercial ones that are really fast are opaque. They don't publish their protocols. They don't expose any internal state. So you can't reason about them at runtime. It's a nightmare for debugging. We had the primary goal of making this understandable like that. The cool side effect of doing this, I love that as a design goal. The really pleasant surprise I found from that is how it enabled so many other things. We now have the fastest messaging system by quite a way because we can easily monitor it and profile it and understand it. We can see all the bottlenecks. So actually building these in as first-class concerns, like making telemetry a first-class concern, I would highly recommend it as a way of working. So how can we pull this together? Well, I'm often talking to people in financial organizations. Banks are one of the worst examples of this, and they want to offload a problem. So they say, if I send a message, is it guaranteed delivery? This is the question I get a lot. Put a little trademark on this, because lots of people say this. They want guaranteed delivery. Well, what does that actually mean? Whenever I hear somebody say that, first thing that screams out to me is, this person has not read any of the formal work in this space because they clearly don't understand it. Because that is something that anybody who's done any formal work here realizes is a complete fallacy. Now, the person who normally asks me this is usually someone who's an architect at a bank somewhere. They probably haven't written a line of code in the last 20 years, if you're lucky. What they're trying to do is absolve themselves from any responsibility in certain tasks. So if they get a product in, this is, if I send a message from A to B, I want to guarantee that it gets there because I don't want the problem. I want it to be your problem. Sorry, that just doesn't work all of the time. To make things completely reliable, you have to have cooperation and collaboration to make that work. The protocol, right up to the application level, has to acknowledge that certain things can happen and be prepared to deal with them. Then you can have a really good way of dealing with stuff. Like, I like to flip this around and sort of say, rather than talking about guaranteed delivery, talk about guaranteed processing of something. Like, take the guaranteed delivery case. So if I have a completely reliable messaging system that delivers once and only once, what happens is after you consume that message and later on you process it and you crash and you haven't dealt with it in a sensible way. As far as the user is concerned, that is not a reliable system. It doesn't matter where you try to apportion blame. The end user cares about the overall service. That means the entire thing end to end has to agree to work in a certain way and deal with certain cases. So we can address that by, for example, if the delivery is idempotent, it may be delivered more than once. But if the application's idempotent, then we don't have a problem. So it's a kind of bigger picture in this. So kind of moving on from that. If we have a means of reliably delivering something, in the case of power outages and crashes, machines bursting into flames, as long as we have a majority of the cluster still functioning, we can still get something delivered. Maybe more than once, that's fine. then what sort of shape are we in? If we can do that, let's talk about the design of that and what can we do. Well, typical system that's going to run is going to have clients. They're all going to send some sort of events or messages or queries to a given service. If you want that service to work well and to survive certain cases, like for example, if I want to switch it on and off again, I want to upgrade it, I need to at least store the data somewhere to have a persistent memory of history. So I'll start off, the first level is I'll store it somewhere on disk. That's a pretty basic step that we need to do. That can be the log of the input messages, works kind of nicely. A single database works the same sort of way. But what if that bursts into flames? What if it goes wrong? The number of times I've had discussions with clients, like going back, I've been writing code professionally now from the beginning in the 90s, and over time I keep finding people going, but our machines are highly reliable. I had one customer who bought this, what they thought was a highly redundant machine that had multiple power supplies, multiple disks, multiple processors, all designed to take up whenever something else goes wrong. Their data center burst into flames. Tough, they didn't have a reliable service afterwards. You need to have more than one thing in more than one location to be truly reliable. So what do we need to do then? Well, we need more than one version of your service. So you send requests to something. It's going to deal with them. It's going to store them safely on disk. It's going to be processed in some sort of service. But we now have a new thing that needs to be dealt with, and that thing is what's going to manage the consensus between having more than one instance of that service. So we end up with a consensus module of some type that exists in there, and it will coordinate to deal with these failure cases and deal with that. Now, 2 is not a very good option. I still keep seeing this a lot. People want to, I want a reliable system, so I'm going to have a primary and a backup. That is not good. What if the network splits between these two? It's the split brain problem. Which one is the leader? Which one is going to respond to the customers or the clients at that stage? It is not a reliable system because you'll end up with issues around that. We need to have some way of, if the network splits or if a single machine fails, we know what's going on. And the simple answer to that is you need at least 3. So in the case of any network partition that will happen, what will end up happening is maybe 2 of them can talk to each other and the third one can't communicate. The 2 of them can form quorum, and then they can continue because they have the majority view on things. Very simple in how it works. Yet I still keep seeing people saying, but we'll save a bit of money. We'll only have 2. It's not a good approach to go with. You need to have at least 3. Maybe 5 if you want even better uptime than that. So we've got to think a little bit differently about this, and then things get to be much more reliable. So I'm going to kind of break this presentation up a little bit. We give out all of our source as open source. It's freely available. You can all use it. There's not even any cost to do that. So I think if I do that, I should at least share some of the pain I go through. So if you get to share the code, you should share a little bit of my pain. Now, I write code in Java and C# and C++ and Assembler and various other languages. Java particularly causes me some pain at times. So I'm just going to pick on Java. You can pick on other languages too, but Java is kind of an interesting one here. So I think we kind of agreed that servers do crash, and that causes a certain set of problems. So let's look at this rather ugly little bit of code and work out what's going on. So it's kind of odd. I'm catching exceptions, I'm ignoring them, I'm doing all sorts of weird things. Now, let's dig in a little bit. So I'm opening a file channel, and I'm opening it for a directory. Not a file, just a directory. But if you know this API, you'll also notice you give it a bunch of options. I'm giving this no options. I'm not opening it for create. I'm not opening it for append. I'm not opening it for read or write or anything. I'm just opening it. And then I'm catching this exception, which I'm deliberately ignoring. And then later on, if my channel is not null, I'm going to call force on it. Why am I doing this really ugly little bit of code? Well, if you happen to be running on a Unix machine, and you go to create a file, and you're going to write data into that file, and you want that to be reliably written to disk, you've got to deal with if it's going to crash in the machine. You want to make sure your data is reliably on disk, so you'll fsync or fdata sync your data to disk, so you're forced it out to disk, so it's not just in your page cache in your operating system. That's kind of great. You can be doing that. But what happens if you created that file, and that file exists in a directory, and that directory structure has not been synced to disk. You can't find the file again. Welcome to the world of lost and found on a Unix system. So what do we need to do is we create the file, and then afterwards we've got to sync the directory to disk as well. Now from Java, there is no officially supported means of doing this. This is a hack that we need to do to be able to write things to disk. Now, if you happen to run in your Java on Windows, you don't have a problem because Windows will sync the directory to disk if you update the directory structure. Unixes tend to not do this by default. So there's differences in the world, and we have to be able to think about these things. It would be so nice if we just had an API that looks something like this, like I want to force a directory to disk, and true to say I want to force the metadata and the data itself, but we don't have that. But we've got var, we've got all the syntactic sugar, but we can't keep our files safe on disk. Come on, what sort of an industry are we? We need to grow up and be a bit more professional. Let's get better at the important stuff. So let's talk a little bit about performance. So the reason we were asked to implement this in Aeron is people wanted a fast clustering implementation. There are a number of very good implementations out there using various protocols, many of them for Raft. They work, they're reliable, they give us good results. Unfortunately, none of them are particularly fast. So if you want to run a financial trading exchange running at hundreds of millions of messages per second and be responding in sort of single or even just tens of microseconds, you don't do it with the existing implementations out there. They're all far too slow, much, much slower than this. So what could we do to get into this space? So let's look at the design and look at what we can do to make this faster. One of the things we've got to fundamentally look at is the whole premise behind RPC-based designs. They cause a lot of failure cases, but they also cause some very significant performance limitations because they couple us temporally to what's going on. So let's explore this a little bit. So if I've got a system, looks like what we've just described, 3-node cluster, and a client sends a message to the currently elected leader. Nice and simple, we send the message to the leader. What happens then? Well, first thing the leader has to do is append it to its own log on disk, so it safely got that message before it does anything else with it. It then needs to send it to the other members of the cluster. And think about the API, append entries, append entries. Most of these things are also implemented over TCP, where we send them to other nodes like this. So you send it to another follower. The follower then needs to append it to disk. And then we need to send it to one of the other followers, which needs to append it to disk. Now think about each of these steps as we're expanding time out. We have to wait on each of these happening, and eventually gets to there. Now, what's interesting at this point is when I've called append entries, I can also pass what is known as the commit position. So you've got concept of two positions in a cluster. There's the appended position and the commit position. The commit position is where you have a majority, or you've reached quorum, that a majority of the nodes have got this already appended to disk. Now, you know whenever you call this node that the majority of the cluster, because you've already got it on the other two nodes, has this message on disk. So it can let this one node also okay to process. Not just that you've got it and you can write it to disk, you can also safely process this, because if there's a crash of any node in the cluster, we can still recover and go forward and have a new leader without losing any data. So you process it in a service. And then it can process it in the leader itself afterwards. So things are happening like this, but this is all taking time. These are network hops, right to the disk, all happening sequentially, one thing after another, all temporarily coupled. This becomes a big issue. Now, what can we learn from other ways of doing stuff? So our modern CPUs are incredibly fast. Let's look at why they're so fast, because there's a lot to be learned from hardware. I keep finding that people are inventing stuff in software thinking they've invented something new and cool, but it has been done in hardware decades ago, and we often just don't learn from our other fields. This is common in all sorts of other fields of science too. You find the physicists learn from biologists, biologists learn from chemists, all sorts of different things. The more we collaborate, often we'll find some cool ways of doing stuff. So, typical CPU is very fast because it runs what is known as an instruction pipeline. So we'll fetch instructions, they're going to be processed. So that's one step in the process. We then need to decode that instruction because our instructions are high level. x86 is a high level language to our modern CPUs. They actually run micro operations, not x86 instructions, so they need to be decoded. We then need to execute the resulting micro operations that come out of that, and then eventually we do a retirement phase. I won't get into that because it's much more complicated. Our CPUs do lots of things out of order and do things with a lot of complexity, so the retirement phase is actually quite complicated in modern CPUs, but so they kind of do these 4 basic steps that may be broken up into other steps. Now imagine if each of those steps took 1 cycle. It would take 4 cycles to process any given instruction in a theoretical CPU. But what if the hardware that done the fetching started fetching the next instruction as soon as it fetched the previous one? The decoder starts decoding the next, and vice versa, and so keep going like this. We could end up overlapping what's going on. So if we were to process 4 instructions, we could complete in 7 cycles as opposed to 16 cycles if we did them all out in time. Now when people tend to program with RPC, they tend to do the same sorts of things, is they stretch out the time with how we work. If we pipeline, we make things asynchronous, we can make things much greater throughput and finish jobs much faster. So we improve the latency as well as the throughput and how we deal with stuff. In a cluster, what would this look like? Well, the leader has to order all incoming messages, so we need a sequence to be deterministic. It needs to log them to its disk. It then needs to transmit them to the other nodes of the cluster. It has to reach consensus on what is the commit position that the cluster can move forward to, and then eventually it can execute beyond the commit position. But if we start doing this in a pipeline fashion, we can get greater throughput and we can reduce the overall latency. This is pretty typical in most games designs and financial trading systems, and a lot of the military systems that are out there. A lot of what we learn in those spaces often doesn't come through to what is normal enterprise software today. It's unfortunate that our industry doesn't share so much, so we don't get to learn. So why I'm a big fan of open source is because we get to share ideas and we can learn and move forward as an industry. By keeping things secret and proprietary, it's very difficult to learn. Humans are great mimics. If we see something, we know we can repeat it and do it better. If you haven't ever seen something, you don't know what's possible to do. So this becomes an important thing we're going forward. So what would this look like in our cluster? Well, let's say we give each component its own thread and they're all communicating with messaging. It's a great thing to dog food your stuff, so you design your system based upon message passing just like it's going to be applied to. And these are all running as independent entities. So what will end up happening is a message comes into the cluster, like before, to the leader. The leader can just broadcast it to everything else that's involved. So forget this whole RPC idea. Just send it as soon as you get it. And if you get another thing, send it again straight away. You don't wait for the acknowledgement of the completion. You send it, and then asynchronously send back what you've actually done. And ideally, batch it back as well. And then you can send out the commit position again of what's been achieved. And broadcast things out, and we can keep going around and completing this model, but basically changing the whole way we work. So break the RPC model down into a pipeline model where we're broadcasting stuff. Then we can achieve a lot more. I'll come on to how we actually do this, but let's just cover a little bit more NIOPing along the way. Now, when you write these sorts of systems, you've got to write bytes a lot. You're writing bytes to disk, bytes to the network, reading bytes from everywhere. And in Java, we tend to allocate a byte buffer, and we put things into a given byte buffer. So we can put in, at an absolute index, a given value. That works absolutely fine. What if I wanted to put a bunch of bytes in at an absolute index into a given buffer? So at a given index, I'm going to put in source bytes for a source index and a given length. I get a red squiggly in my IDE. Why can I not do that? I have to set position and limit, which is not thread safe. I can't use things in parallel. It kind of breaks a lot of programming practices. Surely someone would realize this is a really bad idea and we should improve this API so we can have for multiple threads deal with this in a nice, safe, parallel fashion. Well, other people have thought about this. In 2004, there was a bug raised upon this. This is still not fixed today in our IDE. but we get syntactic sugar, we get var, we get all sorts of fluff. Why can we not have nice things that actually matter? Because most people don't seem to care about what actually matters, it seems, in our industry. Let's move forward and stop doing these things. So, how can Aeron help with the previous problem? What can we do about this? Well, let's change the algorithm a little bit for how Raft works. Now, if you understand the fundamental theory behind the algorithm, you realize there's certain things that can be changed and changed very easily and still be correct. One example is the message index concept. Every message is given a version and you increment the index monotonically. But that implies that whatever is sending to the network and whatever is sending the disk and whatever is reaching an agreement has to understand the protocol that's encapsulating the messages and has to know what length the message is. That means we still have to start unpacking them at a certain level. And all messages aren't equal. Some are big, some are small, some are broken up, all sorts of interesting things. What if we just thought about it as byte index? We break it down where each byte is its own logical message. And the fact that we group those at a higher level into messages from an application perspective, that still works. It's getting the right level of abstraction at the right level point. Now we can have things that write to disk can agree on what's the byte index that's been written to disk, what is the byte index that's been transmitted to the network, what is the byte index we've agreed is the commit position in the cluster. If you can easily do that, this becomes a lot more simple. You don't need to worry about what's inside those messages, even what length they are. You send a packet of data to the network, you send a block of data to the disk. You just need to know how many bytes you've actually dealt with. This makes things a lot simpler. And also, in most of these systems is fundamentally don't copy. So many problems when you start to measure them for where the costs come about is usually copying or cache missing. Now, copying is often because we're doing lots of protocol translation over and over again. Like, I get to measure lots of real-world applications, and from a message or an RPC call coming in from a network, from those bytes arrive to some business logic actually happens. When you profile, it's all in there, and the business logic is usually a rounding error at the end of the day. We spend so much time going from JSON and XML and various other protocols and various ways of doing stuff. Let's not copy all of these things. Let's encapsulate our protocols properly. So does your underlying implementation allow you to add a header to an existing protocol without copying it? So you can do vectored I/O, like gathering and scattering sends and receives as well. It makes things a lot easier. Can you multicast within your cluster? Now, the nice thing is many financial networks support multicast because it's a really nice way of doing stuff. With Aeron, we can multicast. We can also unicast, and we can also simulate multicast using multiple unicast streams. So from a programmer's perspective, it looks just like you're using multicast, but you happen to be using unicast streams underneath. Now, this is typical in sort of cloud environments where they don't allow multicast to work. We can get a lot of the benefits. We don't copy anything except just sending them to the separate sockets, but all the data structures we use, one of the nice benefits is that our data structures are all functional and immutable. They're persistent data structures that can be used multiple times, and we don't need to worry about that. There's no concurrent issues around that. The fact that they're also persistent data structures is we can spy on them on the way out to the network, and that allows us to effectively receive them without actually receiving the data. Think about the leader sending to the followers. Locally, it has to record it to its local disk. It has to process it within its service. If you were to spy on the outgoing data without having to actually receive it again, you've just saved half your network traffic. Simple things like that start to matter. It's overall systems engineering that matters, not very much isolated ways of thinking. To really get performance, you've got to think about systems engineering. And once we start going to the concept of a byte index rather than a message index, we can bound consumption and everything based upon counters. Like if your messaging system allows you to consume up to a given byte index, you don't even care what's inside them. You can have already replicated all the data. You don't even need to do anything with it. You just bound your consumption based on the commit index, which is separately broadcast within the cluster. And that way we can scale and deal with things quite nicely. Once you start dealing with that, you get a thing that comes as a nice side effect called natural batching. So if you broadcast that the byte index has moved on to a certain position, that can mean many messages are now available to be consumed. If you go to write to disk, you're not writing single messages at a time, you're writing batches of messages. You're writing batches of messages to the network. You amortize the cost of that. And the payback works really nicely. So the payback on anything that you amortize, as soon as you go from a batch of 1 to 2, the cost per item is now 50% of what it would be if you're sending them individually. You go to 4, the cost per item is down to 25%. It's a diminishing return. You get the best wins in the first 10 or so elements. In fact, your very best win comes from going from 1 to 2. Batching has a huge advantage just going from 1 to 2. So designing with this sort of ways of thinking, it really helps. And you can apply it at all sorts of levels. So it can be batching your system calls, batching your network round trips, batching your disk writes, or any expensive computations. Design with this sort of thinking is the way to get throughput. And that reduces your latency because it reduces your serialization costs. We get some interesting requirements in these type of systems. As soon as you start building them, a few things start to become very obvious, like timers. If everything that comes into the system is going to change state, it must be a message. That includes time. You cannot read time from reading the normal clock. It has to be pulsed in some way. So it has to enter the system as a message. Now, the way that's normally addressed is people pulse in time events, which is a problem in its own right because you can fill up your log. If you want your time to be quite granular, you need to send in lots and lots of messages. The other thing you can do is manage your own time inside the system and trigger it based upon other events, and that requires timer wheels and all sorts of complexity around that. Make it part of the cluster infrastructure makes things a whole lot easier, and it becomes a first-class concern. So one of the things that we do is we introduced a very simple timer concept. It becomes part of the role of the sequencer. And with the cluster, if you want to set a timer, you just tell the cluster, I would like to schedule a timer. It's going to have a given correlation ID. It's going to have a timeout that it's going to occur at. So that's our first bit. That's how do we schedule it? Nice and simple. The correlation ID is just an opaque identifier for what should be done whenever this event happens later on. You can do whatever you want with that. You can put a function in a map. You can have something that can be triggered based upon that correlation ID later. And then later on, when the deadline has expired, we call back with an on-timer event, passing you the correlation ID and the timestamp that it currently is now. This way, we now don't need to care about having a clock in the system. It becomes really nice for doing things like time travel tests, like let's advance 3 months into the future and see what happens when this future settles in a given financial instrument, or similar things like this. It becomes great for going back and rerunning yesterday. So we have a bug in production yesterday. We get the logs from yesterday, we just replay them, we set a conditional breakpoint in the debugger. When we know that a certain correlation ID or a certain time is going to pass, the debugger just stops at that point, step, 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 there's the cause of the bug, perfectly recreatable. If you have ever worked on one of these systems, for me this is the killer feature for why I don't like to work on other systems is, you can go back when a customer complains about a bug, you just load the code up, you get the logs from the time when they said they had a problem and you step them forward and you can recreate exactly what the customer's seen and there's no confusion around it. It's not like a system that's running 500 threads and everything's non-deterministic and we're trying to guess what possibly happened at that time when the customer's seen a problem. It's something we can easily deal with it. Storage is another interesting thing we have to deal with in the space. If you're going to write logs, where do we store them? How do we ship them around? It becomes an interesting problem. Do we get a distributed file system for this? That becomes complex. Is that going to become cross-platform? One of the things we've built into Aeron right from the start with this is to have a concept of archiving streams. So if you think about a log, it's just an archive stream of messages. Can you store that fast? Can you replay that fast? Snapshots is an interesting problem in this space. So what happens if we can't replay the logs from the start of time? You don't want to do that. If a system's been running for a long time, that's not a practical alternative. So occasionally what you do is you take a snapshot of the system, and to get back to a given state, it's just snapshot on the logs after that given point. The snapshot is just a stream as well. It's a stream of serialized data that represents the state of the system. This is why it's really easy to debug these systems, is you take the snapshots and the logs from production. walk through them, becomes really nice and simple. You may want to do multiple things on those streams. So again, how do we save our infrastructure? How do we benefit from all of this without having too many things? So we can have our system that's going to have lots of services that are running. Do we want to replicate all of this infrastructure? Well, you're running a deterministic log that's going to have a given order. We can just run multiple services off the same thing. Like in finance, an incredibly common thing is we'll run a matching engine for how people are matching orders in a market. We're also surveilling those markets looking for fraud. That can run on a copy of the same stream. In fact, don't even copy it. Use the same way. Remember, we can broadcast this data out to multiple things. It can build its own model, very much like sort of CQRS style view of the world. We can run other systems like risk systems. We can see what's going on, build other models at the same time, taking advantage of all this same infrastructure, including the fact that if nodes die, they can go away. Like we can now get servers that have got tens and even hundreds of cores. Running these things all on the same machine becomes very easy. How can we communicate fast between these nodes on the same machine? Like Aeron can communicate between two processes in different languages in under 100 nanoseconds per message when it's running IPC. It's like making function calls. This sort of stuff becomes possible. It's really easy to do. So kind of one last bit of IOP in here before I wrap up. Within byte buffer, we've got a number of interesting implementations. We have direct byte buffers, we've heap byte buffers, got map byte buffers. So a direct byte buffer is a byte buffer that is managing some memory that is not managed by the garbage collector on the heap. So this is some memory that we can share with another language or with the operating system. Like say I'm going to write to disk or read from disk. I can also have a thing called a map byte buffer where I can map a file into memory and treat it just like real memory and interact with it. Now, a direct byte buffer has a certain set of features. Map byte buffer has got the same features, plus it adds some others. Like I can force the file to disk if I've made changes, so I don't lose any data. Now, I mentioned Liskov at the start of this. Barbara Liskov, who did the work on VStamp replication, which is arguably the first protocol that was out there, she's probably much better known for the L in solid. Liskov's substitution principle. Let's look at Liskov's substitution principle in the case of this. So if I have a map byte buffer and a direct byte buffer, if one of these was to extend the other, which would be the correct approach? Should direct byte buffer extend map byte buffer, or should map byte buffer extend direct byte buffer? Now, the fact that with the substitution principle, you're only allowed to add features. You must be able to directly substitute a subclass for a base class, and it should behave correctly. So a direct byte buffer has less functionality than a map byte buffer. So who thinks 1 is the correct implementation? No. Who thinks 2? Yay, so we've got more people think it's 2. Well, under Liskov's substitution principle, 2 is the correct answer. What do we think the JDK actually does? Byte buffer. I could use byte buffer alone. I think I could put together a full university course on design and use it as an anti-pattern in what should and shouldn't be done. It is just a terrible implementation. So I have to suffer it, so I'm sharing a little bit of that pain. So quickly in closing, where are we at? This is now in production. It's available. You can look at it. We're not officially releasing it yet because we're still doing some performance and correctness testing, mostly because we're just being overly cautious. We know how difficult these things are. We know how difficult it is to get it correct, but it is in production. And one of my customers built this for a bit of fun to demonstrate it to the people he works with, where he used Raspberry Pis to build the cluster, and you can pull power and you can pull leads out, and it works and it behaves and all correctly, which is a kind of really cool thing to do. I didn't even know he did this until he told us afterwards. And it actually runs at pretty good throughput rates, even on the Raspberry Pi cluster. That Raspberry Pi cluster does better than I see most enterprise software actually do in processing these sorts of systems, because it just doesn't waste in the same way as many of the others. So where are we at actually on performance figures? Well, if your network is up to it. Like I'm talking about if you're running things like multicast with Solarflare or Mellanox cards and using kernel bypass, like this is the high end of what finance can do. Is we are reaching consensus on messages in the cluster in tens of microseconds. We are seeing throughput in the rates of hundreds of millions of messages hundreds of thousands of millions of messages per second. It depends on the size of the message because we end up saturating the network. We can very happily run right up to full network saturation at 10 gig. I've been testing on some NVMe storage for writing the logs and the snapshots and replaying them. We can record and we can play back at 2 gigabytes per second. That's not 2 gigabits, 2 gigabytes per second. That is 2 bonded 10 gig Ethernet connections. Most people don't even have that in infrastructure, and we can do that on single machines. That's the sort of throughput and performance figures we're getting. So it's just become a non-issue in many ways for the rates in which we can deal with this. So for me, it's kind of been a really fun thing to work on. I've enjoyed it a lot. I think we should challenge ourselves, but not just challenge ourselves. You learn so much by looking around and looking back. Virtually everything we did on this project has been inspired by work from the 70s, 80s, and 90s. None of it's actually new, it's just been put together in new ways, and it's actually just focusing on what matters and how to do it. And so on that, I'll thank you very much. We're done. Go ahead. So good question. How do we do correctness testing on this cluster? We do it in a number of different ways. We haven't run Jepsen testing. We do plan to. We've actually got our own correctness testing framework. So the two people that are doing the majority of work is myself and Todd Montgomery. Todd's background is he's ex-NASA. He used to do IV&V testing for NASA on things like shuttle, Cassini station, lots of these things. So he's built a little framework that does similar things to what Jepsen can do, but we can run the tests faster than Jepsen because we don't need to, we simulate the network at a higher level to the application rather than actually at the network level just to run more tests. And we're correctness testing with the likes of those. That has thrown up some interesting problems. So we actually will just look at certain sequences of messages that we know cause issues. We make sure they're tested, we make sure they're correct, and we're fuzz testing as well. It's really hard to beat good fuzz testing of things, so just randomly generate sequences and see what happens. It does throw up things, we find things. We would like to more formally prove it longer term, but that will take us some time to get around to that. It's quite an effort to get to there. In the past, used things like spin, and spin is a good way to formally prove something. So our changes to the Raft algorithm would be nice to formally prove those. But I keep finding that that's not where many of the issues are. The real issues come down to we just make mistakes in implementation. We all do. And so even though you may be following a spec that's formally proven to be correct, you can still just miss a knot somewhere, a less than or greater than. It's something that should just be a less than. These sorts of things can happen at times, and just catching them all takes time to flush them out. Hopefully we'll eventually get there, but you can't formally prove a large code base and make sure the actual implementation is correct beyond a certain amount of testing. Okay, any more? Are we done? Cool, no more. Go have lunch, thank you.